All right, so in this video, I'm looking at the problems that deal with section 11.4. That's binomial probability. And these are the ones where we use that formula that looks like this. Probability of that many successes. And then you do n choose x, probability of getting a success, probability of not, and you're going to raise that to the n minus x power. So let's see how that's used. Okay. So the probability of no girls. We're going to think of getting a girl as being a success. So the probability of having no girls would equal 5 children, getting no girls. The probability of getting a girl is 1/2, but we don't want any of those. The probability of getting a boy is also 1/2, and that means the remaining ones would have to be boys. Okay, and so then it's a matter of you just finding that button on your calculator and doing 5 choose 0 times 0.5 to the 0 times 0.5 to the 5th. If you can change it into a decimal, I think it works. Change the fractions into a decimal, I think it works well. What I wound up with is 0.03125. Now, depending on the question, it might ask for it as a fraction or a decimal. So I'm going to use my F to D button. Looks like this on mine. And I'm going to just change that back to a fraction. Turns out to be 1/32. And I might have gotten that directly if I had just entered 1/2 in there instead of 0.5. I would have come up with the fraction. All right, so the probability of exactly one girl or the probability of exactly two girls is done in a similar way. We're just going to adjust the formula. So let's get those formulas in there. So we want one girl, but then we want the rest to be boys. Okay, so 5 choose 2 on number 6. The third one, we want 2 girls, and this should be down just a tad. It's not times, it's 5 choose 2. Probability of getting a girl is 1/2. The probability of not getting a girl is 3. So we're going to work that out. Okay, so we're going to do 5 choose 1. And let me just keep the 1/2 in there this time. To the first times 1/2 to the 4th. And either use your fraction key or use division to do that. So as a decimal, if you did it as a decimal, it would be this without rounding. Or if you did it as a fraction, oops, let me get that again. It would be 5/32. Okay. And that's because this part was 5, and then this would be 1/2. Then 1/2 times itself 4 times would be 1/16. And that's what gives you the 5/32. Okay. So the probability of 2 girls, when you do 5 choose 2, you get 10. 1/2 times itself is 1/4. 1/2 times itself 3 times is 1/8. So that winds up giving me 10/32, which I can reduce and get 5/16. And you can type it all in one step and get the 5/16. And you might also have it as a decimal since they didn't really specify how they wanted it, and you would have been okay either way. So this one would have been, as a decimal, it would have been 0.3125. Okay, and either of those forms are okay because they didn't really say what they wanted. All right, now here's a tricky one. Okay, the probability of getting less than 2 girls is not just P of 2. See, that formula only works when you have exactly this number. Okay, exactly that number of successes. So what you have to do if you want the probability of less than 2 girls would be no girls or 1 girl, but you can't even have 2 girls. So you would come in and you would take the probability of getting no girls and add to that the probability of getting 1. Okay, and using the formula. If you hadn't been asked that earlier, you would have had to do the formula for both, and you'd get 6/32, which when you reduce it would be 3 over 16. Okay. And that's the same as 0.1875. And either this or this would be okay. Either one. All right, when you do at least 4 girls, the problem there is we haven't already calculated these. So we'd want 4, but we could have 5. At least 4 means 4 or more. So we'd have to get the probability of 4 girls, and we haven't already done that. So we would do 5, choose 4, 1/2 to the 4th, times 1/2 to the 1st, because the one that's not a girl would be a boy. And then we'd come over here and do 5, choose 5, 1/2, we want them all to be girls, times 1/2 to the 0. And we'd get these numbers and add them together, okay? So 5 choose 4 is 5, okay? So you could do that. You could just do 5 and then go in there and double check, and you'll see 5 choose 4 is 5, okay? Then 1/2 to the 4th power would be 1 over 16, and then that would be 1/2, but I actually can just type that in with the times sign in between everything, and I would wind up with 5 over 32 for that one, okay? And then 5 choose 5. 5 choose 5 is going to wind up being just 1, isn't it? Let's see. 5 choose 5, just double check it. You get a 1 there. 1/2 to the 5th power would be 1 over 32. 1/2 to the 0 power is just 1. So we get that plus 1 out of 32, which gives us 6 out of 32 again. Just happens. It does. There is a reason. We're getting a little symmetry going on here. And that winds up being 3 out of 16. Now, you could do a probability tree. You could come in and do that probability tree for the first child, the second child, and so on. But you're doing 5 kids, so it would be a pretty huge probability tree, but you would get the same answers we're getting here. But the whole point of the probability formula is that you don't have to do the tree anymore, okay? So that was problem number 6. And on number 6, the probability of a success happened to equal the probability of a failure. But on number 7, it's a little different. Okay, here we have a company that manufactures calculators. They do it in batches of 64. And there's a 4% rate of defects. Okay, so they do 64 calculators at a time. And the rate of a defect is 4%. Now, 4% means 4 out of 100, which turns out to be 0.04, okay? All right, now it says find the probability of getting exactly 3, and I'm going to define a success as being a defect. See, we're looking for the probability of getting 3 defects. So define, let X equal getting a defective calculator. Define a success as being getting a defective calculator. And then what I'm being asked is what's the probability of having exactly 3 of those? So there's 64 in a batch. I want 3 of them to be defective. The probability of getting a defective calculator is 0.04, and I'm trying to get 3 of them to happen. Then right here, I want the probability of not getting a defective calculator. So if I have a 4% chance of being defective, then there's a 96% chance of not being defective, right? That would be 96 out of 100, and that would equal 0.96. See, these two right here have to add up, have to equal 1 when you add them up. Okay. All right, and then 3 of them were defective, which means the rest of them were not. And then I'm just going to go ahead and type all that into my calculator in one step. You do the same, and then we'll check each other. So 64 choose 3 times 0.04 raised to the 3rd power times 0.96 raised to the 61st power. All right, and so this one is a decimal that kind of goes on forever. So I would look at what they wanted me to round to, and we don't really know. So let's suppose they want us to round to the thousandths, 3 decimal places. Oops, it's 10. This is what I see on my calculator, like that. So if they want me to round to here, I look at the 0, and I would say it's closer to 0.221 than 0.222. And usually they have you do it as a decimal on these, and they'll specify what they want you to round to. All right, now let's look at number 8. On number 8, we had a multiple choice test with 10 questions. There's 4 answers for each question, and we want to know the probability that a student will get at least 6 answers correct. So what we really want to find is the probability of getting exactly 6. But then we're going to find the probability of getting exactly 7, exactly 8, exactly 9, and exactly 10. And then we'll just add all of those once we get those figured out. Now, sometimes, depending upon how they do it, okay, this one, it's almost equal both ways. But if they had the probability of getting at least 9 right, then you would have only had 2 to do, right? And so you would definitely have gone that way. But if they had said the probability of getting at least 2 right, I would have had to do 2, 3, right? A whole bunch of them, right? All the way up to probability of 10. And I could do that, and that would be my answer. But if they wanted the probability of at least 2, then you might want to think, okay, well, that means 0, 1, or 2. Wait, I said it wrong. That's not what I meant. If they say the probability of at least 2 and you want a shortcut way of doing it, you could get the probability of no calculators being defective and the probability of 1, and you could add those up and then take all of that away from 1. That's what I meant to say. Because there's so many of these to do, I could do that, but I'd have to calculate, probability of 2, 3, 4, 5, all the way up to 10. What I could do is say, well, what's the probability of having no defects or 1 defect? And I can take that away from 1, and that would equal this same thing that I had here. So it's just a shorter way to do it. With this problem, it didn't help you to think that way, okay? So you would just have to go in, and you'd have to do, how many questions? There's 10 questions. Okay, so 10 questions, choose 6. The questions have 4 answers, so the probability of getting it correct would be 1 out of 4. Oops. 1 out of 4. And we want 6 of them right, which means 3. The probability of a failure would be 3 out of 4. That means the rest of them have to be wrong. Okay, and you would set up that same thing on all of these. 10, choose 7. Probability of getting it right would be 1/4. I want 7 of them right, but then that means 3 of them would be wrong, and the probability of being wrong would be 3 out of 4. And you would keep doing that similar setup on all of them. Okay. So what you're going to do is calculate each of these, and then once you're finished, you're going to add them all up. I'm going to get rid of this piece now because that's not something we're doing. And once you calculate each of these, the probability of at least 6 right would be all of these answers added up. So all right, so you'd have none wrong. So then you're just going to calculate each of those on your calculator. All right, so when I did that, I should have had little squiggles on that, on each of these. So I got approximately 0.0162. Then 7 was approximately 0.0031. Then I got about 0.0004. Not very likely that you'll get 8 correct just by guessing. And then for 9, 0.000. I kept a little more accuracy so that it wouldn't round to be 0.004. And then the last one I kept a lot. It was 0.000. That's 4, 5, 6, 5, 1, 2, 3, 4, 5, 6, and 9, 5, 4. So when I add all of those up, I wound up with about 0.0197. And if they wanted me to round to 3 decimal places, then I would bump this up, which means since that would become 10, I would have to bump that up. So I would get 0.020. Okay. And problem number 8 was the last one that dealt with the binomial probability formula. So I'm going to stop sharing on that and get this one posted.